in digital circuits, what is a hazard? How can it impact our circuit's operation? Let's talk about it. So in general terms, a hazard is a chance of being injured or harmed, right? But what does it mean to a digital electronic circuit? To appreciate that, we have to go into a couple of terms, right? And the first is steady state behavior. Steady state behavior of a circuit is the value of that output after the inputs have been stable for a long period of time. But before a circuit's output becomes steady state, it has to go through what is called a transient behavior, right? And more or less, that transient behavior is more or less that unstable behavior before reaching to steady state. Now let's understand what is a glitch, right? And a glitch is very undesirable. Basically, it's a short pulse produced in the output during that transient state, right? And if a circuit has the possibility of producing a glitch, the circuit has a hazard, right? Now let's talk about two types of hazards. The first one is basically a static one hazard, right? And the static one hazard is the possibility of receiving a zero glitch, right? When you expect a steady logic 1 output. Then we also have the static zero hazard, which is the possibility of getting a 1 glitch when we expect a stable, steady logic 0 output, right? So how do we identify hazards in a digital circuit, right? The easy way to do that is, well, there are two ways. First way is actually analyzing the circuit, looking at all the parts within the circuit and determining which are the slower parts, which are the parts that are slower than the others, and then determining, you know, what could result in a hazard. But the best way and easier way is using a Karnaugh map. So let me show you how to do that. So if we wanted to go about and determine the hazards that exist in a digital electronic circuit built utilizing this Karnaugh map, it's very easy, right? This Karnaugh map will represent a particular output, right? Let's say F, A, B, C, D, right? And let me write that on top of the paper here. F, A, B, C, D. So this Karnaugh map will represent that output. Now if you want to find out what hazards will be affecting that output, is very easy. First thing we do, we go about using the normal Karnaugh mapping method, right, to determine the least amount of large circles that we can now find. And after doing that, we will now find out the expressions for each of those circles, right? So let's go about doing that. First thing, we find a square or circle here, and let's immediately find the expression for that square or circle. We look in this direction, right? And we realize what is common to all of those ones are B equals 1. And B equals 1 is going to give us the expression B. We look downwards, vertical, at the C and D, and we see what is common. We see C equals 0 is common. So therefore, that expression for C equals 0 is C prime. We go ahead now and we do another circling. We see there are 4 ones here. We circle them. It's easy for us to find the expression for this circle or square, and I'm going to use square and circle interchangeably. the expression for that, we see that what is common is only C equals 1 and D equals 1. So therefore this expression here is going to be CD. Now, before even doing any work on hazards, right, what's going to happen is this is going to produce a circuit that is going to be affected by hazards. So we would have gone about getting the expression F A B C D is equal to B C prime plus C D. Right? Let me write it out again so that it doesn't look confusing. Without considering hazards, our expression, our output FABCD is equal to B C prime plus C D. This is not resulting in a hazard-free circuit. This circuit exists. A lot of hazards exist in this circuit still, and we need to discover what hazards exist and then rectify the problem. Right? So just reminder, the result, the minimum SOP for FABCD is equal to B C prime plus C D. And this, the circuit, the output that results when we utilize this expression and we develop a circuit, a logic circuit that implements FABCD, that output is not hazard free. So how do we discover hazards? It's very easy. So let's get to it. So to discover those hazards, we have to look at the Cannon map a little closely. And if we are seeing any neighboring ones, any ones adjacent to each other that are not in the same circle, those ones will result in hazards. So let me point out in this Cannon map, there are ones that are adjacent to each other but are not in the same circle. And those ones are this one, all right, this one, this one, and this one. Those are 4 ones that are in the same, they're adjacent to each other, but they are not in the same circle, and they will result in hazards. Alright, so a general rule is when you want to find out what hazards exist in a circuit, you have to look at the Cannon map, look at the ones. Any ones that are next to each other but are not in the same circle will result in a hazard. How do we actually, solve that situation? We have 4 ones. How do we result in that? How do we actually resolve the hazard? Well, it's easy. We have to make sure that all of those ones are in the same circle. So what we need to do is we need to actually introduce another square or circle that encloses all of those ones. Like that. We have to introduce another square or circle that encloses all of those ones. Right? And what we have to do next is to find out the expression for that square or circle. Looking in the horizontal direction, what is common to all these ones is B. Looking downwards, what is common to all these ones is D. So the expression for that square is BD. And what that term is, we have to include that term in the expression F A, B, C, D equals B prime, B, C prime plus C, D. We have to add that expression B, D to our minimum SOP. And that term is called the consensus term. Right? That new expression, that expression for that new circle that we use to enclose the neighboring ones that were adjacent to each other is called the consensus term. And by adding that to our minimum SOP, yes, it's going to add hardware to our circuit. It's going to add, in this term, it's going to add an AND gate to our circuit, yes, but it's going to guarantee that our circuit is hazard free. So that is how we more or less eliminate a hazard from the circuit by adding the consensus term B, D. So your design is not complete unless it is a hazard-free circuit that results. You need to eliminate all hazards. Hazards will negatively impact your circuit. There may be times that you're actually designing and implementing any circuit and you testing and you're realizing that the output behavior is not what you expect. You expect a logic 1 in certain cases or logic 0 in certain cases and you are not getting it. And it could very well be because of the presence of hazards in your circuit. So you need to get rid of hazards. Utilize this method that I explained to you in this episode, and that is it, right? But make sure that all hazards are removed. Many times we tell students to come up with the minimum SOP for particular outputs, right? But one thing to bring to their attention is, although the minimum SOP is, they get this particular expression, they need to also, if they're going forward for a serious design, make sure that it's hazard free, and they may have to add consensus terms, hence making the minimum SOP expression lengthen. So I'll see you all on another episode.